Today, as I said, we are going to talk about some examples of what we learned so far after the midterm, actually, and get ready for the final. Now, let's start. The first concept that we learned was the Root-Hurwitz criteria, which was a criteria that we used for analyzing the stability of the system without going through the whole time domain or frequency domain response. Now, let's go for an example of K over S squared plus S plus 1, S4 plus 2S cubed plus 3 plus K S squared plus 1 plus K S plus 1 plus K. Now, we wanted to see how we can develop the Root-Hurwitz table, and using that, start to find if the system is stable or not. Now, what we were gonna focus is the denominator. So we don't care about the numerator, we just focus on the denominator and develop the table, the Root-Hurwitz table for our denominator. Now, it's the fourth order, so we are gonna have the row S to the power of 4, S cubed, S squared, S, and S to the power of 0, which is 1. Okay, so we have to go from the highest order all the way to the order of the 0, which is 1. Okay, now we learned if we want to develop the row for S4, we are gonna start with the coefficients of S4, which is gonna be 1. We are gonna skip one term and write the next one, which is 3 plus K. Again, we are gonna skip one and land to the last one, which is 1 plus K. Now, for next row, again, we are gonna use the coefficients of the S3 for the first column. So we already considered S4, so we don't input the coefficients. Here, we start with S cubed, and the coefficients is 2. We skip 1, then the next one is 1 plus K. And if we skip the next one, we don't have any term, so it's 0. Okay, now, that was the first two rows. We learned that we can develop the rest of it using the component in the first two rows. If you remember, we named these extra columns as, for example, B1, B2, B3, and the next column was C1, C2, C3, and the last one is going to be D1, D2, and D3. Now, we learned that if we wanted to calculate the B1, the formula for B1 was minus determinant of the first column of the first row. So it's going to be 1 and 2, and then the second column in the first two rows, which is going to be 3 plus K and 1 plus K. And we are going to divide that by the bottom left component, which is 2. Okay, so divided by 2. Now, if you do the determinant, which you know how to do, for this B1 case, we are going to end up in 1 over 2, 5 plus K. Are you good? So, here, we are going to replace the B1 with its value which is 5 plus k over 2. Now for B2, again, we have minus determinant of, now for B2, we have again the first column of the first two row, 1 or 2, and then the second column is going to be the third, the second column of the determinant is going to be the third column of the first two rows, which is 1 plus k and 0. Divided again by the bottom left component, which is again 2. Now, we can run the determinant and find that it is going to be 1 plus k. So let's replace that with 1 plus k. Now, for B3, okay, for B3, we are going to use the first column. So B3 is going to be minus determinant of the first column, 1 and 2, and the fourth column, which you don't have it, so it's going to be 0. So it's going to be 0 and 0. And you already know we have a column of the 0, so the determinant is going to be 0. Are we good on that? So let's replace that. So our B3 is going to be 0. Now, we have to go for the third row. For the third row, I am going to clear up these so I can actually have enough space. C1 is going to have the same kind of like formula. So it's going to be minus determinant of. Now, here we use the second and third column. Are we good? So it's going to be 2 and 5 plus k over 2. And the second column of the determinant is going to be, again, second column of the second component of the second row and third row. Are we good? It's the same kind of like formula as B1, but shifted one row. So it's going to be 1 plus k, 1 plus k, divided by the bottom left. So it's going to be divided by 5 plus k over 2. Now, if you do that, if you do the calculation, it's going to be k squared plus 2k plus 1 over 5 plus k. Let's replace that. K squared plus 2k plus 1 over 5 plus k. Now, look at the C2. It's the same situation as we had for the B3. It's going to be the denominator of the formula for C2 is going to be the determinant of the first components of the second and third row, okay? And the third component of the second and third row, which are 0. So C2, same situation, is going to be 0. And same goes for the C3. So you can imagine that. So it's going to be 0. Now, for D1, again, the formula is the same, minus determinant of the first component of third and fourth row. So 5 plus k over 2, k squared plus 2k plus 1 over 5 plus k. And the second component, the second column is going to be 1 plus k and 0. 1 plus k and 0. Divided by the bottom left, which is k squared plus 2k plus 1 over 5 plus k. Now, if you solve that, you are going to end up with k plus 1. Okay, so we are going to replace that with k plus 1. And D2 and D3, same situation, is going to be 0. 0 and 0. Are we good so far? Now, the situation that we had for analysis of stability was if the first column of our table would change polarity, okay, from positive to negative or negative to positive, then our system is unstable. Now, let's do that. And remember, K is always a positive number because it starts from 0 and goes to plus infinity. We don't have minus K. Okay? The negative number for the K. Okay? So this is positive. This row is positive. 2 is positive. If K is positive, this one is going to be positive. Again, is K is positive number. This is positive, 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 positive. So it's also positive. And same for here. So we don't change polarity. That means this specific example is going to be safe. Any question? Are we good? Now, I'm going to erase that for the next Root-Hurwitz example. Just tell me you are still recording. Yes. Okay, the next example, we are going to go a little bit more wild. Our transfer function g of s is going to be 1 over s to the power of 5 plus s 2s to the power of 4 plus 2s cubed plus, this is 2, 4s squared plus 11s plus 10. Now, again, we are going to develop our table. Now, we have a fifth order, so we are going to have s to the power of 5, the row s to the power of 4, to the power of 3, 2, 1, and 0, which is 1. Are we good? Now, let's put the component and actually develop the table. We are going to start with s to the power of 5 for the first row. The coefficients of the s to the power of 5 is 1. We skip 1, then we have 2. Skip 1, we have 11. And if we skip this one, we don't have anything, so it's 0. For the next row, the s to the power of 4 has coefficients of 2. We skip this one, we have 4. We skip this one, we have 10. We don't have anything, so I just put 0. You can ignore those zeros and don't put it in the table. I just put it so you know when we have a determinant that is going to equal to 0, why it's happening. Okay, so for S4, we are going to use the formula that we had. Okay, now look at the determinant. For first component, it was the determinant of first component of the first and second row, so 1 and 2, determinant of that, and 2 and 4. So the determinant of that is going to be 4 minus 4. So it's going to be 0. Now we have a problem. Okay, so we said if we have, now let's actually run the whole thing. Now the second component is going to be determinant of this divided by 2, so it's going to be 10 minus 22. Okay, did I use that right? 10 minus 22, which is 12, divided by 2, which is 6. Okay, so the next one, again, this one and this column, so it's going to be 0. Is that clear what happened? Let me actually write that. So this B1 is minus determinant of 1 and 2 and 2 and 4. Okay,
-6
over 2. No, I'm gonna show you. This is gonna be, see, it's 10 minus 22, which is minus 12.
and then divided by 2.
We have another minus here,
Oh, yeah.
so it's gonna be 12 over 2. So this is gonna be 0, B1, then B2 is minus determinant of 1 and 2 and 11 and 10 over the bottom left one. So 10 minus 22 is minus 12, minus 12, plus 12 divided by 2, 6. And here, for the third one, we have B3 is minus determinant of 1 and 2. And the fourth component, which is 0 and 0, divided by 2, which eventually is going to be 0. Because the determinant of that is 0. Are we good? Now, we already said that if we have, because our stability analysis was over the first column, 0 is neither positive or negative. So we can consider the polarity for that. So that means we can actually analyze it for stability. The trick that we did was to replace the 0 with an epsilon. Okay, so we are going to do that. So I am going to erase that 0 and put simply epsilon. Now, let's develop the fourth row based on that. Now, beside having a 0 and problem with the stability analysis, okay, if we wanted to calculate the C1, this is going to be a determinant, okay, and divided by the bottom left, which is if the 0, that means we can't actually calculate C1 because it's undefined. It's going to be infinity. Are we clear? So we don't want 0 in the first column. Now, if we have epsilon instead of 0, now we can calculate the C1, C2, and C3. Now, C1 is going to be the determinant of 2 and epsilon and 4 and 6, actually minus determinant, divided by epsilon. Are we clear what happened? Same formula as B1, okay? So it is going to be 4 epsilon minus 12 divided by epsilon. Now, the second one is going to be 2 and 0, epsilon and 10 divided by epsilon, which is basically, and we have a minus for the behind the determinant, so it's going to be 10 epsilon over epsilon. This one is 0 because we don't have anything here, so it's going to be 0. For the next row, we run the same kind of analysis, and we are going to have 10 epsilon squared plus 72. I'm not going to go through the details, so you know what's happening. 12, and then we have zeros. And for the last row, we are going to have 10 and zeros. Are we good what happened? Is that clear what happened? Now, we said if we want to actually run the stability analysis, okay, we have to consider epsilon as a very tiny positive number, okay, and see what's going to happen. Now, if epsilon is positive, meaning we have a positive epsilon, first row, the first component of the first column is positive. Next one is also positive. Third one is epsilon. We consider it positive, so it's positive. Then we have here, which is 4 epsilon minus 12 over epsilon. Okay, if it's a tiny positive number, that means in a numerator we have minus 12. In a denominator we have a tiny positive number. So eventually we have a negative number. Here, this is positive, so it's going to be positive, but very small. So denominator would end up at 72, and denominator is 12, so it's positive. And the last row is also positive. Now, here, we have a change of polarity. So, on a stable system. Now, if you consider epsilon as a negative infinitesimal number, again, we have positive for the first component, positive for second component. Now the third component become negative because we consider that as a negative tiny number. Negative. This one become minus 12 over a negative number. So it become positive. This one is 72 over 12, positive. And this one, the last one is also a 10, so it's positive. Again, we have a change of polarity here. So no matter what polarity we consider for epsilon, this system is gonna be unstable. Any question? Are we good? Now, I don't want to solve any example for this next case that I want to say, but remember, if anything happened during our Root-Hurwitz table development, that we have an entire row equal to 0, okay? Let's say I'm gonna just put a Root-Hurwitz table of like S4, S3, S2, Sn 1, and this is like 1, 2, 3. This one is 1, 2, 2. Let's go to this 4, 2 minus. Why did okay, and then 0. This is 2, so this becomes 0. This is 0 minus 0, so it becomes 0 and 0. Now we have the entire row of 0. Are we good? Now, the trick that we used was to develop the row above that 0, 1. So S cubed, the row S cubed is going to be 2S cubed plus 2S. Remember, we skip one order, okay? 2S, and this is 0, so plus 0, it doesn't matter. Are we good? Now, what we want to do for developing the row for S squared is to simply get a differential in respect to S. So we are gonna consider, we are gonna take, let's say this is this is G2 of S. So G3 of S is gonna be the determinant of the G2 over S, which is 6S plus 2. And then we replace that.
S squared.
S squared, sorry, thank you. Then we replace that in our 0 row. So we are gonna clear this one. The first column S squared is gonna be 6. And then we skip that one. We skip the S to the power of 1, which we don't have that. And then we have a 2, and the rest is 0. Now we can continue with our development. Is that clear what happened? We had an entire row of 0. We used the row above it. So the row above it, if you develop a transfer function from S cubed here in this example, this is going to be 2 times S cubed. We skip S squared, 2 times S, and then 0. Here. Okay? Then we take a derivative in respect to S. So it's become 6S squared plus 2. Now, the row S square is gonna be the coefficients of S square, which is 6. We skip the first order, which is the coefficients of S. We don't have it actually, but we have to skip. And then the next component is gonna be the order of 0, which is the constant number, which is 2. And we don't have anything after that, so it's 0. Now we solve the problem. We can continue for developing the next rows. Are we good? What happened here? Any question about the Root-Hurwitz technique? No? Go on.
You explain, like, okay, I get how you have the 6 for the first column in S2. Why is 2 in the second column?
This is, if you wanted to rewrite that to have all the orders,
Yeah.
this is gonna be 6 S squared plus 0 S plus 2.
Right, there's no
6, we skip 1, and then 2.
Got it.
Any other question? No? Are we good? Okay, I'm gonna move on to the root Locus, if you don't have any questions. Let me check if it's still recording. Yeah. Now, for the root Locus, we are going to solve an example that our g of s, h of s is going to be, see, it's g of s, h of s, okay? Remember that. It's going to be k over s plus 3, s squared, this is our example, s squared plus 2s plus 2, okay? And we wanted to find and basically find the trajectory using the root Locus method. Now, first thing, we want to first have our estimate, and let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. Doesn't matter what here. Now, the first step for the root Locus was to replace all the poles of the denominator, all the zeros of the denominator, which is the poles of our GH function, okay? On the estimate, we have one pole at the origin, so one pole here. Let me use another color. This is not showing itself. Then we have one pole at -3, which is 1, 2, 3 here, -3. Now, if you solve this for zeros, okay, I think you can imagine that it is gonna be s plus -1 plus j and s plus -1 minus j. Okay, so we are gonna have 1j here and -1j and -1 minus j here. So this is -j -1j. Are we good? So now we place our poles in our system. What was the next step? Anyone remember? What was the next step that we normally take to draw the trajectory?
Find the real axis segments of the root Locus.
The segment of the real axis that includes in the trajectory. And our rule was we have a negative feedback. I have to mention that actually. We have a negative feedback. That means the segment that have odd number of poles and zeros to the right of it is included in our trajectory. This part from 0 to infinity is not included. This part has one pole to the right of it, so this part is included. And from -3 to minus infinity, that segment is not included in our trajectory. Are we good? Now, our trajectory, which is basically k from 0 to infinity, we said you start from the pole and end up to the zeros. Are we good? So we are gonna start from the poles and end up to 0. I'm not gonna start from these poles because I still don't know how they would leave the initial poles. Okay, so we have 4 poles, no zeros. That means we are short for 4 zeros. But all those trajectories should end up in the zeros. Are we good? So that means there are zeros in infinity that these are going to end up to. What was the next part? We need to find the asymptoid lines, okay, in order to see how these trajectory would move toward zeros in infinity. Now we have 4 extra poles. That means we need 4 extra lines. 4 basically asymptoid lines. Now, the asymptote line had 2 characteristics. One was where in the real axis, all those lines would cross the real axis. Remember, we call it delta A. And the formula was the sigma of the poles minus sigma of zeros divided by the number of the poles, absolute number, okay? Number of the poles minus number of the zeros. I put absolute because it doesn't matter which one is bigger. If we have like a extra zeros or extra poles, okay? So basically, the denominator is going to be 4, we know that, okay? And the nominator of this is going to be -1, -3, okay? And then minus 1 plus j, and then -1 minus j. Are we good? I just add those poles together. We don't have any zeros, so it's going to be 0. In this example, actually. Any questions so far? Go ahead.
Where did you get the first -1?
Oh, sorry. Thank you. It's going to be 0, actually. Thank you. Are we good? Now, if you do the math, these 2 j's are going to cancel each other out. And basically, actually, because we have a symmetry. So if we have a complex value for poles, we are going to have the conjugate of that. So when you want to like calculate the summation of the poles, you can ignore the imaginary part because it's going to be canceled by the conjugate of that number. Okay, so it's just the real part that matters.
What notation is that?
This number.
No, I'm talking about the first one.
This one?
Before like
This one? Delta A.
That's
Delta A, which is the point that the asymptote line would cross the real axis. Now, do the math is gonna be minus 1.25. This is minus 5/4, which is minus 1.25, which is somewhere here. Are we good? Now, another part was the angles of those four asymptote points. So the formula for the angle was the odd number of 180 over, again, the number of the poles, absolute value, number of the poles minus number of the zeros. Now, this part was a little bit tricky. We need 4 lines, that means we need 4 angles. Very good. So we are gonna change the D to find all those 4 angles. So, and we said D is gonna be equal to 0 and then plus minus 1 and then plus minus 2 all the way to infinity. And we are gonna move forward until we reach the number of the theta or phi or angles that we need, which in this case is 4. Now, if D is equal to 0, then this is gonna be 180 over 4. Are we good? Which is gonna be 45 degrees. We put the degree part of. We wanna be precise. Now, we are gonna move forward. If D is equal to 1, then it's become 3 times 180, okay, which is 270, right? No. Which is gonna be what? 420, right? Divided by 4, which is gonna be this. This is 1, which if you calculate that is gonna be 135 degrees. Then we put D to equal to minus 1 by 3. You do the math is gonna be 225. D to the power of D equal to plus 2. And then the last phi that we need, the last angle that we need is gonna be 315 degrees. So now we have the 4 degrees, the 4 angles that we need. So if you do that, the asymptote lines are gonna be like this. Are we good?
-1, the angle is -45.
Which one? This one? Yeah. If it's -1, this one is gonna be 180. -180, yes. Thank you.
Well, I can do 1 and run the D.
We put D equal to 0, 1, -1, and 2 in this formula and solve for the phi, the angle. So if it's 0, it's become 180 over the numbers, which is 4, the difference of polar and zeros. If it's 1, it becomes 3 times 180 divided by 4. If it's -1, it's become -180 divided by 4. If it's 2, it becomes 5 times 180 divided by 4. Now,
Theta 4 is 2 to 5.
225. Okay. So our asymptote line are gonna be crossing on minus 1.25 here with the degrees that we find. Are we good? Now that means our poles are gonna touch these lines when they move out. Now we are not still done. We need to basically calculate, okay, we need to calculate the angle of the departure, for these two, and the point that these two leave the real axis. Okay. Now, we said for finding the values, the point that these two leave the real axis, okay, what we need is to first find the function of k based on s, okay, k of s, and then take a derivative and solve for z. What was the reason behind that? Because we know that the trajectory is start from 0, k0, okay, and move forward. So the point that these two poles are leaving the real axis is the maximum k in the part that they still are in real axis. So it's a local maximum. Are we good? So if it's maximum, that means the derivative should be equal to 0. Now, let's do that. We're finding the function of the k based on s, and regarding actually function of the k and having s as variable, we said we are gonna use the denominator of the overall transfer function. Okay, remember our transfer function of overall system considering the feedback was the g, okay, 1 plus gh. So we are gonna focus on the denominator. We have the gh, so it's gonna be, the denominator is gonna be 1 plus k divided by s plus 3 and s squared plus 2s plus 2. Now, if you do that, if this one become s let me actually skip one place. So if this is the function, okay, we can move that 1 to the left hand side of equation. So actually k over that denominator become equal to -1, and then we can multiply both sides by the denominator. That means k will be equal to minus s plus 3 s squared plus 2s plus 2. Now we have a k as a function of this. Okay, taking a derivative, the derivative of the k in respect to s, you need to do all the multiplication to find the actual k in this like a standard equation. But if you do that and take a derivative, it's going to be -4 s cubed plus 3.75 s squared plus 4s plus 1.5. Okay, and we want to put this one equal to 0. Okay, the condition is this one becomes 0. And then we solve for the s's that satisfy this condition. Now, again, if you do that, then the s's that satisfy the condition is a third order, so we are going to have 3 s's. The s's are going to be S1, 2, and 3 are going to be minus 2.3 and then minus 0.7 plus minus J 0.36. And this is also a 2. Sorry. Now, we are looking for the S, okay, that is on the real axis because we wanted to see when the poles are leaving the real axis. These two are complex numbers, so these are not going to be our answer. Only the first S that we find, which is a real number, is satisfying what we want. Is that clear what happened? Any question? No?
Oh, no, I'm just trying to read the,
This is minus 2.3, this is minus 0.72 plus minus J 0.36
and that's for solving the S, is that for taking the derivative?
for this one. Yeah, put that equal to 0.
Is it negative K or negative 4?
Minus 4. Yeah, we don't have a K here because we find the K as a function of S. Okay, let me actually rewrite that to avoid confusion. Although the first one was more close to what the 4 would look like. Okay, are we good? Now, so the point that we are leaving the real axis is minus 2.3, which is going to be minus 1 minus 2.3. It's going to be somewhere here. So these two poles are leaving the real axis at that point. That means the trajectory would leave the real axis and at the infinity would eventually touch the asymptote lines. Are we good? Now, these two poles also have to touch the asymptote lines at the infinity. Okay? But the question is, with what angle these two trajectories would leave the poles? We are going to consider one of them. The technique that we use for finding the theta of how it would leave the initial pole, the trajectory would leave initial pole, was to consider a very close auxiliary pole. We're going to use that, okay? So we are going to consider an auxiliary pole here, okay, which the distance is infinitely small. That means it's basically at the same place, okay? And the line that connect these two poles with each other would basically have the same theta of the departure. Is that clear what happened? Are we good on that?
Read that last line again.
In order to find the departure angle, we are going to consider the absolute next point in a trajectory, which is another pole with infinite small distance from the initial pole, okay? And whatever theta the line that connect these two poles is going to be the departure angle. Now, we already know if that ancillary pole is actually a pole, which this is our assumption, and it should be, okay, let's say S1. If S1 is actually a pole, it should satisfy the conditions of the poles that we have in the beginning of the Locus. What was the condition? The condition was if we connect all the poles to that S1, so we have this like a vector, okay? This line, and then this line, and then this line. Okay, and we have another line connecting the -1 plus j to that S1 too. Okay, so we have 4 lines. There are 2 poles, so we can see that line right now. The theta of these vectors, these 2 vectors, if we add them, should be an odd multiple of 180. That was the condition. That if it was satisfied, then we had a pole. You remember that? Now, the theta of this vector, you can find it using a tangent inverse of, this is -1 and this is +1, okay? So the tangent inverse of that complex value, the vector, could be the phi1. Are we good? So we have phi1 here. This one is almost perpendicular to the real axis. Are we good? So this one is going to be 90 degrees. And again, we can use this one using the tangent inverse rule. Okay, and find the, let's say, phi2, and this is phi3. I hope you can read that. And the last one, which is the theta that we want to find, okay, is our departure angle. I'm gonna use another notation, and I'm gonna call it the theta of departure. Now, the summation of these should be 180. Are we good? That means the theta d is going to be 180 minus phi1 plus phi2 plus phi3. And that way we can find the departure angle. If we find the departure angle, we can find, I didn't calculate the actual number, but I know like what it kind of should look like. Okay, so it's gonna be something like this.
So we're gonna do something like this on the exam. Oh, we got to do something like this on the exam.
Yes. If it asks you for a departure, you have to calculate that. And this is, you can actually calculate that this is the 1 and 1. So this one is gonna be 45 degree. Right here. So this is gonna be 180 minus 45. This is 90, and this is 1/2, the tangent inverse of 0.5, which I think is gonna be 60 degree? No, 30 degree. 30 degree, I'm not sure. So we have 45, 30, and 90. Okay, and then 180 minus that is gonna be
Can you explain like how you or why it's point marked as S1 to determine the like how did you choose the point S1? Where did you find the
It should be a pole. We wanted to see how the trajectory would lead.
Yeah.
Okay, so let's say I'm gonna zoom in into that point, the pole, the initial pole. Let's say this is the pole that we have as -1 plus j. This is 1 minus plus j.
okay.
It's gonna leave, the trajectory is gonna leave with a certain degree. Let's say is like here. Okay, now if it leaves like that, that means we have a pole very close to that initial pole, -1 plus j, that is on the trajectory. Now, I'm gonna consider this pole very close to that one. Okay, I'm zooming.
Yeah.
So we can consider there is a line. We can assume instead of a curve, we can kind of like run it like a regression kind of like type of thing and replace that curve with a line because they are too close to each other. So whatever degree that line has is going to be equal to whatever degree the departure has. Is that clear? What happened?
I was just wondering like why the -1 plus j instead of the -1 minus j. Or could
Either
just either or.
Either way, because we have a symmetry. So if you choose one, the other one should mirror that. You don't need to calculate the departure for all of them. You know what I'm saying?
Yeah, yeah.
So because we have a symmetry, you can choose one of them and then assume the other one as a mirror of the one that you calculate. Any other question?
Last thing. What did we do with the S1, 2, 3, and we that part of the equation S1 and 2, S3? Yeah, to kind of determining the S's after taking the derivative.
This is the denominator of the overall transfer function.
Yes.
Okay. We are going to use the denominator, okay, in order to find a function of the k based on s. So it's 1 plus k, whatever. That means cos k over that whatever function that we have here is going to be equal to -1.
Yes.
Make sense? So if this is equal to -1, you can simply multiply by the denominator both sides.
Okay.
Then k, one part is going to be only k, okay, and the rest is going to be a function of s. So what we're going to do is to use the denominator of the transfer function and try to isolate k, keep it at one side of the equation, and move all the other terms to the other side.
So you're taking the derivative of dkds and then equal to 0 and finding the s to get your k.
Yes. Now, if we have a function of the k, and we know this departure, the point that we leave the real axis is a local max.
Yes.
Okay.
Ew.
Then the derivative of this one should be equal to 0. So we take a derivative, we put it as 0, then we have the s's that satisfy that condition. Now, we know that we are going to have a point and real axis. So we have 3 s's, this is a third order, but 2 of them are complex numbers, so it cannot be.
Those are close to S1, B, S, or those are.
Yes, like for example, yeah, this you can see that. You can see that. See, this is also a local mean and local max. These are these two numbers.
Okay.
You know what I'm saying? So, but we don't care about those. Okay, right now. Now, you might kind of like that's actually a very good point. I wanted to like add that. When you wanted to like draw the Root-Hurwitz, okay, you might think, okay, how I know this curve is like this? You can use these two zeros because they are going to be, again, max mean value of the trajectory. And see, these are like this point here, which is the minimum, of the trajectory, and this point here, which is the maximum of trajectory, are gonna be these two S's. So then you have a point to find out how the curve would kind of like react. Are we good? If we don't have these two S's, that means we don't have mean and max on those two curves, so it's a loss strip.
Wait, so those S's came from this K function?
The derivative of, yeah, we take a derivative of that K function, put it as 0. If we do that, it gives us all the local or global max and mean of our trajectory. Okay, so one of them was in a real axis. That means it's the point that we leave the real axis. We might have more than that, which is the complex conjugate numbers. Okay, for the point that we leave real axis, we don't need that, but these are not useless. We can use them to find how the curve of these two complex poles would look like. But eventually these two are also going to be mean and max. You see what I'm saying? So minus 0.72 plus J 0.6 is going to be somewhere here. Approximately is going to be lower than that, okay? But somewhere here, and the other one is going to be somewhere here. So you know you have a max and mean on those points.
And how do we determine the asymptote lines?
Asymptote lines, we need two values, two type of values. Okay, one is when the asymptote lines were in the real axis, the asymptote lines would cross the real axis, which the formula was, let's say this function, this point, we call it delta A. The delta A was the summation of the poles minus summation of the zeros divided by the number of the poles minus number of the zeros. Are we good? Is that clear? So you add all these poles and subtract all the zeros. In this example, we don't have a zero, so it's 0. Okay, in this summation becomes 0. Here we have a pole at 0, a pole at -3, one at -1 plus j, and one at -1 minus j. Now those two j, as I said, normally cancel each other out because we always have conjugate complex numbers. Okay, so you can simply add the real part of all the poles. Okay, which is going to be -5, and then the difference between the number of the poles and zeros are 4. We are short for 4 finite zeros. Okay, so it's going to be 5/4 minus 5/4. Are we good? And which is 1.25 in this example, and you can point it now. It's not just that, each of these lines would have a theta because we need to exactly find what are these lines and where are them and how the trajectory would be, what is the slope of those lines, which we can define it by the theta of those lines. And what we had for the phi was it should satisfy the condition of the odd multiple of 180. And we have 4/1, so we can divide that by, again, the difference between the number of the poles and zeros. And this d would go from 0 to ±1 to ±2. And we move forward until we reach the number of the theta that we want. In this example is 4. So we move from 0, ±1, ±2, until we have our 4 thetas. And then when we have it, we can draw those lines. Let me. It comes from the angle of the departure. The angle of departure in that way.
First I go this line, right? Go to calculate that.
That consider my bad. Okay, so you calculate all of that, and then when you have the angle of departure, the last thing you do is to draw those trajectories. Make sense? You see, you have an angle of departure, like some degrees, okay, that leaves here, and you know you have a mean and max here, so it should leave here and end up at the mean and max of the curve. Okay, is going to be here. That means these poles moving that way. Make sense?
No, but I make that. Why you so- Sorry.
It should, first of all, it should leave with a 90 degree. Okay, always we leave the real axis at 90 degree plus minus. Okay, and we know if we leave that at k equal to infinity, we have to touch the asymptote lines. If these two poles touches those two lines, these two should touch these two lines.
Yeah.
Very good. Any other question? Oh, I'm looking at that clock. That clock doesn't work. Or we are already out of time. If you don't have any question, we can finish the session. If you have any question, don't hesitate to ask. Are we good? Perfect. In the next session, we are gonna talk about the frequency response. We gonna go over again of how we can draw both plot and the Nyquist and see how we can define using the Nyquist to see what is the stability situation of our system. Okay, thank you very much and have a great rest of the day.